All right, good deal. 9.1 is on sequences. This chapter is different. It's different from any other chapter we've covered. We will use some integrals in here, but it's on sequences and series, okay, which is something different than what we've been doing so far, in either Calc 1 or Calc 2. We're going to start off with sequences. A sequence is a function with a domain of the positive integers and a range a subset of the reals. Well, that's not very helpful, actually. Basically, what a sequence is a list. For example, this is a sequence. 1, 1/2, 1/3, 1/4, 1/5, etc. Okay? These are the elements of its range. The domain is 1 goes to 1, 2 goes to 1/2. These are the positive integers, okay? That's its domain. 3 goes to 1/3, 4 goes to 1/4, 5 goes to 1/5, etc. Now you're going to be asked to do a couple of things here. One thing you may be asked to do with a sequence like this is find the nth term of this sequence. What would the nth term of this sequence, a sub n, be? 1 over n is correct. Now you could write it as a sub n equals 1 over n. You could also write it as this. They both mean the same thing. The nth term of that sequence is 1 over n. Okay? So the 50th term, 1 over 50. Okay? Immediately obvious. The other thing you're going to be asked to do is determine whether the sequence converges or diverges. Okay? Very similar to what we did with improper integrals. The sequence converges to some real number L if the limit as n goes to infinity of that nth term is L, a real number. Okay. If that limit does not exist, otherwise it diverges. So if the nth term has some limit, no matter what it is, okay, as long as it has some limit, some real number limit, the sequence converges to that limit. Okay? So you're going to be given things like this. You're going to be given something like, here's a sequence. Let's say it's 1/2, 2/3, 3/4, 4/5, etc. And you're going to be asked to find the nth term and determine whether it converges or not. Okay? Anybody with the nth term?
N minus 1 over n.
N over n plus 1. You could do n minus, what'd you say, n minus 1 over n, as long as your n starts at 2. If you start your sequence at 2, but generally it's going to be understood to start at 1 unless otherwise stated. Sometimes they'll tell you to start somewhere else, but generally it's going to be starting at 1. N over n plus 1. Okay. Does the sequence converge? Converge or diverge? Well, I already started writing it. All right. Does it converge or diverge? Well, geez, I started writing converge, so it probably converges. What does it converge to?
1/2.
No, 1. Because the limit as n goes to infinity of this nth term is 1. Now, how do you determine that? A couple of different ways. This goes back to Calc 1. We have polynomials with same degree. Ratio of leading coefficients is 1. But you know what? The easiest way is L'Hopital's. You got something going to infinity, something going to infinity. And you may protest and say, Burns, These are discrete functions. These are not continuous functions. We don't have a derivative here because this thing is defined for 1, for 2, for 3. This is a bunch of points, and they don't have derivatives, a bunch of points. Derivatives are a continuous function, but you know what? You're allowed to connect all the dots with a continuous function and use L'Hopital's. If L'Hopital's converges, okay, if that limit exists, then this one does too. Yes?
I mean, it's the same thing, either function, we still get the same point.
Yeah. What we're doing is, it's understood, this would be x over x plus 1, continuous functions, x and x plus 1, they have derivatives. This doesn't have derivative, but if you connect the dots, it's fine, okay? And you're allowed to do that. Now, some things you're going to come across here. All right, this was pretty simple, it seems to me. They're increasing by 1. But they're not always going to just increase by 1. You're going to have things like this. Let's say we have these terms. Okay, let's go with 2 over 1, 4 over 4, which would be 1, 8 over 9, 16 over 25, 32 over 36, which does simplify, okay? Divide by 4, you get 8/9, etc. What about the terms of this sequence? Anybody come up with the terms of this sequence? What's it?
The top has an n times 2. Right?
No.
It's n squared.
Which one? Numerator or denominator? What are you doing?
Numerator.
What?
Denominator is n squared.
Denominator is n squared. You got 1 squared, 2 squared, 3 squared, 4 squared. Wait, where's the 4 squared? I skipped it. What a jerk. All right. Oh, man. All right. 2, 4, 8. This should have been 16 over 16. It was supposed to be n squared. What's the numerator? 2, 4, 8, 16, 32. What are those? Powers of 2. Yeah, that kind of a thing. Okay? That's kind of a thing. Okay? What about this sequence? Is it converge or diverge? Now, this is going to diverge because you could use L'Hopital's, but that means taking a derivative of 2 to the x, which is 2 to the x times the natural log of 2. It's one of those you use logarithmic differentiation. But here's the bottom line on this. You've got a numerator increasing faster than the denominator. Exponential functions increase faster than polynomials. This n squared is increasing pretty fast. But you know what? Exponential functions increase even faster. Think about this. When you take the derivatives, numerator and denominator, using L'Hopital's, this is indestructible, the 2 to the x. Think of it as e to the x. The derivative of e to the x is e to the x. No matter how many derivatives you take, that's not going away. You're going to get e to the x. The same is true for 2 to the x. The first derivative is 2 to the x natural log 2. The next derivative is 2 to the x natural log of 2 squared. And then 2 to the x natural log of 2 cubed. The 2 to the x is indestructible. But what about the n squared? One derivative gives you 2n. The next derivative gives you 2. You're done with those derivatives. They're stuck at 2. Okay? I mean, that's it. As far as you go with L'Hopital's. Numerator's continuing to increase without bound, but the denominator's stuck at the constant 2. Okay? So, you've got a numerator exponential function increasing faster than the denominator. This thing will diverge because it will go to infinity. Does it make sense, that what I'm saying? That relative rates of increase is going to play an important role in not next class, but the class after. When we talk about power series, how fast these things are increasing is going to be important. Okay? All right, another thing you're going to see is this kind of a thing. What about this? 1 over 1. Let's just make it simple because otherwise I'll screw it up. 1 over 1 again. 1 over 2. 1 over 6. 1 over 24. 1 over 120. These are things we're going to run across a lot. Can anybody come up with the nth term for this one? These numbers is 1, 2, 6, 24, 120.
N times 3?
What is it?
1 over n times 3?
No. These numbers are factorials, okay? And we're going to run across factorials a lot. N factorial, exclamation point, means n minus 1, n minus 2, 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1, okay, is 120. You have to know that 0 factorial is equal to 1. Okay. Your calculator knows that. Your calculator will have factorials, exclamation point on there. You give it a 0 factorial, it will give you 1. It knows what it is. Okay? So what's the formula for this one? The nth term would be 1 over n minus 1 factorial. Okay? When n is 1, you get 0 factorial, which is 1. When n is 2, you get 2 minus 1 is 1 factorial, which is 1. When it's 3, you get 3 minus 1, 2 factorial, which is 2. And then you get 3 factorial, 6, 4 factorial, 5 factorial, etc. Does this sequence converge or diverge? It converges, because here we have one where the numerator is stuck at 1 and the denominator is increasing without bound. Okay, that limit clearly is going to be 0. As a matter of fact, if you've got any kind of a sequence and it's decreasing but staying positive all the time, this is called monotonic, okay? It's decreasing, but it's staying positive, it's got to converge. It has no choice but to converge. Same way, if it's increasing all the time, but there's an upper bound, here, let me show you one of those. If you had something like this, let's see, so you have 15 and a half, 15 and 3/4, 15 and 7/8, 15 and 15/16. Can somebody give me an expression for the nth term of this thing? Ugh, I don't know. Can you do it?
15 plus n over n plus 1.
Yeah, it's not going to do it. It's a good shot, but it's not going to do it. Actually, you're probably better off thinking about it this way. 16 minus a half, 16 minus a fourth, 16 minus an eighth, 16 minus a 16th, etc. What about the nth term for this sequence, which is the same as this one?
Is it 16 minus 1 over 2 to the n?
You got it. Yeah. Okay. Here's a sequence, okay? What it's doing is increasing all the time. 15 and a half, 15 3/4, 15 7/8. But it's bounded above by 16. It can't get past 16. You know what? That sequence converges. It converges to 16. Okay? And you can see it by taking the limit as n goes to infinity here. This will go to infinity. This will go to 0. That sequence is converging to 16. All right, there's one other thing you should know before I let you loose here, and that's the other thing is something like this. Let's suppose you have this one, this sequence, here's the sequence. Can someone come up with the nth term of this sequence?
It's going to be negative 1 to the n plus 1.
Oh, right on, Dylan. All right. When n is 1, what's that?
Z. We do that in his computer class.
Oh, do we? Oh, shoot. Okay. You're so modest. You could have said yeah or something. So I thought of it all by myself. All right, but anyhow, when n is 1, you get negative 1 squared, which is 1. When it's 2, you get 2 plus 1 is 3. Negative 1 cubed is negative 1, etc. What happens is this goes back and forth between 1 and negative 1. Does this sequence converge? No, it does not. There is no limit here. Okay? It does not converge. Okay? It does not converge. It's interesting, if you go to number file, .com, they give a little talk on this sequence. Actually, he's talking about the series, the sum of all these, which is what we're going to talk about on Thursday.
Is it not zero?
What's that?
Is it not zero?
No, well, see, this is what happens. It's kind of cool. If you arrange them this way, you get 0 plus 0 plus 0, etc. You get all these zeros. So you might think the sum would be 0. Okay? You would think so. But if you would arrange it this way, these are all zeros. You get this 1 left over, and that sum is equal to 1. And then he goes through a cool little proof where he shows that the sum could be 1/2 as well. And so you got all kinds of possibilities. The fact of the matter is, the series diverges, does not go to any one particular sum. Okay, it's diverging. The sequence also diverges. All right, so you got some factorials in there, some pluses and minuses for alternating, those things alternating, powers of 2, powers of 3. You're going to have to take a look at some of these and see what you can come up with. Try the homework, ask questions on the homework, and we'll go over that. And then Thursday, we're going to do whatever I said on that piece of paper there.